think it's time for a brief recap of where we are, so we can put the Kalman filter, which we're about to discuss, into context. So the first filter we discussed was the Wiener filter, and it minimized the expected value of the error squared. As a practical matter, this filter works in a stationary environment. It requires a significant amount of knowledge, namely Rx and Rdx. And implied in this is we need to have a target or desired signal dn. Okay, the solution to this system is what we called the normal equation. Or Wiener-Hopf equation. And the resulting filter is often discussed as the Wiener filter. Although that term is more often applied to a filter that we haven't yet met, we will talk about later. The Wiener filter that we often use is actually in the frequency domain, and it's defined a little bit differently. But for now, that's a good summary of what we've got. The next, we actually, I guess we should go back. We had two different ways of finding the solution. The solution could be found by direct inversion of Rx or by gradient descent. Next was the Wiener or the LMS filter, which also minimizes the expected value of e squared of n, but built into it and fundamental to the solution is that it uses gradient descent. And often people use the word steepest descent for that, but it differs in the gradient descent for the Wiener filter in that we approximate the gradient with respect to w of the expected value of e squared of n with just the expected value, or rather the gradient of e squared of n. And so we get a different estimate at each time n as we get different errors. Like the Wiener filter, we require a target signal. We've seen in some of our examples that target signal may actually be derived from the input signal itself in some way, and so it can be quite flexible in how it's derived. But notably, we do not require Rx or Rdx. This one works on a sample-wise basis, and in particular we have a gradient descent step, just one, for each new sample. This one implicitly estimates correlations from the data, and so we don't need to have them in advance. Next, it works in less stationary environments. I know stationarity is a binary determination. Either something's stationary or it's not. But when I talk about less stationary environments, I'm talking about something whose statistics change over time, but in a reasonable way. Obviously, if every sample we had different statistics, this would fail. But if the statistics change gradually or occasionally, that works. We also discussed many variations. The most, I guess, effective or popular and used one is the normalized LMS algorithm. But we also talked about variations that are more or less computationally efficient. Then we spent the last series of lectures on the recursive least squares algorithm. And this one actually, before we get to recursive least square, let's talk about the affine projection. The affine projection algorithm has a different criteria. It minimizes the weight update to hopefully get a smoother weight update, subject to an exact prediction of the desired signal. Now, as you recall, this was how we set up the problem. Then we added the very common variation that we can relax this. I guess I'll put that over here. Can be relaxed using a small update step, like we did with the LMS algorithm. This filter works in less stationary environments. And notably, it's kind of embedded in there, but this is not working on expectations. This is working on data. So this is operates on data with no approximations. As we did with LMS. Rather, it's minimizing a squared error. Or eliminating. A squared prediction error. This one also requires that we have dn. Now we can talk about the RLS algorithm. The RLS algorithm, like the affine projection algorithm, does not operate on expectations. Rather, it minimizes the squared error. And we define that error as the sum over all samples as a weighted squared error, where it's an exponential weighting giving higher weight to the most recent. So for this filter, like the non-relaxed affine projection, the error is minimized exactly for each input sample. It too requires a target or desired signal dn, and it also works in non-stationary environments as long as the changes are slow enough and lambda is small enough. So notably, all of the above are solving the normal equation in some way. For example, Wiener LMS approximates the solution. RLS solves the normal equation recursively and exactly, but using numerical estimates effectively of Rx and Rdx. The furthest from this family really is the affine projection, which is minimizing the squared error, but with other constraints. The most important part about the affine projection is that, like the RLS, it is minimizing squared error based on the data and not based on expectations. The next thing we talk about is going to be the Kalman filter. Kalman filter is in a different family of filters, if you will. It starts, as did the Wiener family of filters, by minimizing the expected value of the squared error. Some of the characteristics are: it operates recursively on the data, it works in non-stationary environments, and most importantly, most significantly, it does not require d of n. In place of that, it does require a model for the system. So in our next lectures, we will begin the development of the Kalman filter and its analysis. This is probably one of the most important developments in filtering of all time, as the Kalman filter provides an excellent way to track systems and predict in the presence of observation noise, incomplete observations, and unknown driving noise. It was originally developed for tracking, for example, aircraft spotted using radar. So we'll use a few examples like that, but it can be applied to countless different applications.